everyone, and welcome to chapter number 1 in the three-phase induction machine course, the rotating field theory or the rotating field concept. This chapter is not a long chapter, it consists of 2 videos, but what we are going to cover here, the types of electromagnetic fields in electrical machines in general, and the rotating magnetic field concept in particular. So once we finish this chapter, we're going to identify different types of magnetic fields, explain, analyze, and interpret how a rotating magnetic field is produced in three-phase systems. And we can elevate that one to multi-phase systems, something like three-phase or multi-phase induction machine. So in video number 1, we are going to cover the definition and conditions of the rotating magnetic field. What are the types of electromagnetic fields in electrical machines? We have 4 types: stationary field, pulsating field, rotating field, and traveling field. Our main target is the rotating field, but we are going to have a highlight about each type. Let's start by the stationary field. To have a stationary field, you need a north pole and south pole, as we can see here, and all the time the flux is going from north pole to the south pole. So these flux lines in the green arrows will cut the rotor conductors, as we can see here. A good example for that one is a DC machine. But how do you get the North Pole and South Pole? Either using permanent magnet or a coil carrying current, like what we see here. Right? So this current I, we're going to produce a flux going from North Pole to the South Pole. If we have XY plane where that one represents theta, and that one will be the magnitude, or the y-axis will be the magnitude of the field, we have what we call it a pot shape, so constant flux under the pole, as we can see here. Because that one is in north, so we consider that one is positive field, and that one will be into the south, so that one we consider it negative field. Another type of fields will be pulsating field, and pulsating field can be expressed as f function of theta and time t, F maximum cosine theta cosine omega t. What we can see here that at certain instant of time and for certain theta we have F maximum, so the field is going to increase and decrease in its position, as we can see here. So that one is increase and decrease, so that one causes something like a note here, so that one will be increasing and decreasing but in its position. And a good example for that one, something like single-phase AC motor, single-phase induction motor. Please note this equation. That one is something like cosine, cosine, but one of them is function of theta and the other one is omega t. Regarding the rotating field function is f of theta and t equals f maximum sine omega t plus or minus theta. This means that the field can rotate clockwise or anti-clockwise, as we can see here. This field is suitable for three-phase induction motors, synchronous machines, three-phase synchronous machines, but I need you to look for this function here. Let me take that one, that's f equal f maximum sine omega t minus theta. So use trigonometric functions. That one can be written as f maximum sine omega t cosine theta minus cosine omega t sine theta. If you look for that one is a pulsating field, and that one is another pulsating field, and that one is a rotating field. So rotating field can be constructed from pulsating field and vice versa. Regarding the traveling field, so the traveling field is identical to the rotating field if it's three-phase, but that one is for linear machines, something like linear induction motor. So far you didn't answer this question, how is the rotating magnetic field produced, or how do we create a rotating field or a rotating magnetic field? The answer is, if a balanced three-phase supply with frequency Fs applied to a symmetrical three-phase winding, a rotating magnetic field of a constant magnitude and running with synchronous speed will be produced. There are a lot of questions here. We need to answer them one by one. What are they? What is meant by a balanced three-phase supply? What is meant by a symmetrical winding? What are the conditions of the three-phase winding? What is the synchronous speed? So we need to answer these questions one by one. So what is meant by a balanced three-phase supply voltage? If you remember in Chapter 0, we had a revision about three-phase systems. If we have three voltages are shifted in time, please remember this word, shifted in time, by 120 degrees, where VA of t equals V maximum sine omega t, VB of t equals V maximum sine omega t minus 120 degrees, and VC equals V maximum sine omega t plus 120 degrees. Or minus 240 degrees, they are the same. So we have the same amplitude but shifted in time by 120 degrees. We can say that we have a balanced three-phase supply voltage. The next question, what is meant by a symmetrical three-phase winding? If we have three-phase winding, we didn't answer the question what are the conditions or what are the conditions for the three-phase winding. If we have three windings, each of which has the same impedance Z, we can say that we have a symmetrical three-phase winding, where ZA equals ZB equals ZC equals Z. Let us answer the third question, what are the conditions of three-phase winding, or how to construct a three-phase winding? We need to satisfy three conditions here. Each pole should accommodate all phases, the phase displacement between adjacent phases is 120 degrees, and the start and finish of each phase is 180 degrees. So each pole should accommodate all phases. We know that the machine is constructed from number of poles, even number. So we have North Pole and South Pole. Under each pole, we should see phase A, B, and C, either go or return. For the second condition, the phase displacement is 120 degrees in space. If you remember in the previous slide, for the first question, the voltages are shifted 120 degrees in time, but here we need to put the winding 120 degrees in space. And for the last condition, if we start phase A at a specific slot, after 180 degrees in space, we are going to have the finish of phase A. Now we answered the question, but actually the answer is not 100% correct. That one is correct only for two-pole machine. If the number of poles is more than 2, we need to modify some words here. So let's start by two-pole machine. If we have a two-pole machine like this one, we have 180 degrees for North Pole and another 180 degrees for the South Pole. We're going to start phase A at 0 point, so the return of phase A will be after 180 degrees in space. And phase B should be after 120 degrees from phase A, and phase C will be another 120 degrees from phase B, or 240 degrees from phase A. We have 180 degrees should accommodate all phases, so we are going to divide that one by 3, so we have what we call it here spread angle. So the spread angle per phase is 60 degrees in space. So here we have the waveform for the MMF, or the magnetic field. So we have under the North Pole, we have something like positive sign, and under the South Pole, we have a negative sign. So we have something like sine wave scanning from 0 up to 360 degrees. But please, I'm going to add here, even I write it, but I'm going to add it from pi, 0 to pi, that one will be the North Pole. From pi to 2 pi, that one will be the South Pole. So we are going to scan from 0 to 2 pi, one full cycle, north and south. So that one is the two-pole machine. Can you explain more for the two-pole machine? We need to understand that one. This is a two-pole machine. We have north and south pole. So we have a sine wave for complete cycle here from 0 up to 360 degrees in the space, or we can write that one from 0 to 2 pi. From 0 to pi, we have positive part of the sine wave under the North Pole, and from pi to 2 pi, we have the negative part of the sine wave under the South Pole. So we can see the distribution under each pole, A, B, C. So we have here A, C dash B, and here we have A dash C, B dash. We know that the electrical machine is something like a cylinder, so we're going to take a side view for that one and make it like a circle. So if we start A at this point at 0 degree, so A dash will be here after 180 degrees from the start of A. And the start of B will be after 120 degrees from the start of A. And definitely the return of B, or the start of B dash, will be after 180 degrees from the start of B. The start of C will be after 120 degrees from B, or 240 from A. And the return of C will be after 180 degrees from C. So under North Pole we have A, C dash, B. And under the South Pole we have A dash, C, B dash. So back to the conditions. Under each pole we should see all the phases. So here we have AC dash B, here we have A dash CB dash. And the phase displacement between adjacent phases A and B will be 120 degrees. Between B and C, 120 degrees. Between C and A, we have 120 degrees. The start and finish for each phase, AA dash will be 180 degrees. BB dash, we have 180 degrees. CC dash, we have 180 degrees. We need an example how to assign the start and finish for a real model or a model for a machine with certain number of slots. Let's see in the next slide this example. Example number 1. For a 24 slots 2-pole machine stator model, we're going to build a stator model using wood, as we can see here, rather than iron, to explain the idea for winding arrangement. So we need to assign the starting points of phases A, B, and C. We need to calculate the number of slots per pole per phase and calculate the slot angle. This is a stator we are going to look for, 24 slot stator, and that one is identical to the real stator from iron, but that one I built it from wood to explain this example for you. That one is the stator length L, and we have here 24 slots. We have North Pole and we have South Pole. So if we say that one is the North Pole in this sign, that one is the South Pole. So per pole we have 12 slots for the North Pole and we have another 12 slots for the South Pole. So number of slots per pole is 12. So how we are going to start winding this machine or this stator using the 3 phases? So here I'm going to start by slot number 1. So this one is a slot number 1. I'm going to start phase A. But we have 24 slots here. We have 360 degrees in the space. So the slot angle, that one will be 15 degrees. So that one is 15, 15, 15. So 15, 30, 45, 60, 75, 90, 105, 120. So we can start phase B at slot number 9. So if you notice, I use a color code red, yellow. So definitely phase C, I'm going to use the blue. I'm going to count another 8 slots. 1, 2, 3, 4, 5, 6, 7, 8. Here will be the start of phase C. So that one will be slot number 17, the start of phase C. So under North Pole now we have A and B. But the condition said that under each pole we should see all phases. The return of phase C will be 180 degrees from that one. So this one will be C dash. So we have A, C dash, B. So now we satisfied the first condition. Each pole should accommodate all phases. And the second one, the start between adjacent phases is 120 degrees. And the start of each phase, start and finish, will be 180 degrees. So if phase A starts at 1, so the return of phase A will be at slot number 13. 12 multiplied by 15 degrees give you 180 degrees. So if you look here for phase A, scan 4 slots. 1, 2, 3, 4. 4 multiplied by 15 will be 60 degrees. 60 degrees will be the spread angle, as explained to you, the spread angle per phase. So how many slots per pole per phase? We have 12 slots per pole. We have 3 phases, so that one will be 4 slots per pole per phase. Turn back to our example. Here we can summarize the results. We have number of slots 24. Number of slots per pole 24 over 2 will be 12 slots. Number of slots per pole per phase will be 12 over 3 equal 4. We are going to use the symbol Q for that one. So Q is the number of slots per pole per phase equal 4. And slot angle psi will be 360 over 24, give you 15 degrees. So the spread angle sigma will be psi multiplied by Q will be 60 degrees. Let us repeat the analysis for 4-pole machine instead of 2-pole machine. P equal 4. And please note that I'm using P as a symbol for the number of poles. Please bear in mind that some textbooks use P or 2P, it depends. But here I'm using P. So let's look for our machine now. We have north, south, north, south. So we are going to divide our 360 degrees to 4 quarters, each carry a certain pole. So if we have the machine like this one, we have north from 0 to 90 degrees in space, and then we have another south from 90 to 180 degrees in space, and that one represents complete cycle, which is from 0 to 2 pi. And this is why I emphasized before to use both of them, pi and 90 degree or pi and 2 pi for mechanical and electrical degrees. So what mechanical and electrical? It's first time to hear this word. So in space we have here from 0 to 180 degrees mechanical, but that represents 360 degrees electrical, 2 pi. So from 0 to 2 pi we have one complete waveform, and from 2 pi to 4 pi we have another complete waveform, which is 360 degrees in space. So we need to apply the conditions. How to apply the conditions? Each pole should accommodate all phases. So we are going to furnish this part from 0 to 90 degree, which is from 0 to pi here, 180 degree electrical, by phases A, B, and C either go and return. And from pi to 2 pi here, we are going to do the same. Also, if we're going to start phase A here at 0 degree, the start for A dash should be after 180 degree electrical, which is 90 degree mechanical. And the start of phase B from phase A should be 120 degrees from phase A electrical, which is 30, 60, that one 60 degree mechanical. So that one 60 degree mechanical, and that one will be 120 degree electrical. So we have a relation between electrical angle and mechanical angle. Can we see this relation? Yes. So look here, theta electric equal P over 2 theta mechanical. So if we have here 90 degrees mechanical, so 90 multiplied by 4 over 2 give you theta electric, which is 180 degrees. 180 degrees mechanical, so 180 degrees multiplied by 2 give you 360 degrees, which is 2 pi. So 60 degree electrical divided by 2 give you 30 degree mechanical, which is a spread angle. Still the spread angle is 60 degrees, but electrical. And in the space, that one is 30 degrees, right? Mechanical. So 120 degrees electrical here, something like 60 degrees mechanical. If we're applying the equation, 120 degrees divided by 2, which is 4 over 2, give you mechanical 60 degrees in the space. So now, if we like to run this machine for 8 poles, 16 poles, 12 poles, we need to consider this equation that theta electric equal P over 2 theta mechanical. Considering the conditions that each pole should accommodate all phases, the start and finish between adjacent phases is 120 degree electrical. And the start and finish for each phase is 180 degree electrical. And these are the two words missing from the conditions I give you before, or I gave you before. This is why I said that these conditions are not complete up to the moment. So now we generalize the case. Whatever the number of poles, we need 120 degree electrical and 180 degree electrical. Let us repeat the previous example for the same 24 slots stator model we see here, but this time for 4 poles instead of 2 poles. So we need to assign the starting points of phases A, B, and C. We need to calculate the number of slots per pole per phase, and we need to calculate the slot angle. This is the model we used before for the 2-pole machine. This side, 24 slots for 2-pole machine. So I'm going to use this side for 24 slots 4-pole machine. So we have here 24 slots. So the slot angle psi will be 360 degrees divided by 24. That one will be 15 degrees. Same like 2-pole machine. But how many slots per pole? In the 2-pole machine, we have 24 over 2 give you 12. Here we have 24 divided by 4 give you 6 slots per pole. We have north, south, north, south. So we are going to have here 1, 2, 3, 4, 5, 6 slots per pole. How many slots per pole per phase? Q equals 6 over 3 equal 2 slots per pole per phase. So slot number 1 and slot number 2 are for phase A. 3 and 4 another phase, 5 and 6 another phase. So if we start phase A at slot number 1, so phase B will start after 120 degrees. So that one is 15, 30, 45, 60 degrees mechanical. Multiplied by 2, theta electric equal P over 2 theta mechanical. So theta electric equal 2 multiplied by 60, 120 degrees. So phase B starts at slot number 5. And then phase C will going to start at slot number 9. So where is the return of phase A after 180 degree electrical? So here we have 90 degree mechanical. If we multiply that one by 2, so at slot number 7, we are going to start A dash. When we are going to continue in this pattern, we are going to have C dash will be at slot number 3. Under each pole, we have here all phases, A, C dash, B. And we are going to have that one the same for this pole and this pole, this pole and this pole. Right? So now we satisfy all the conditions. Each pole accommodate all phases. The phase displacement will be 120 degree electrical, and the start and finish of each phase is 180 degree electrical. Back to our example here. We have these values. Number of slots is 24. Number of slots per pole is 6 compared to the 2 pole is 12. Number of slots per pole per phase is 2 compared to the 2 pole is 4. Slot angle is the same 15 degrees, but the spread angle is 60 degree electrical. 60 degree electrical, same like 2 pole machine. Before we leave these examples, that 24 slots is suitable for 2 pole machine, 4 pole machine and 8 pole machine. But if you like to wind this machine as 6 pole or 12 pole, you might need something like 36 slots. I'll leave that one for you to configure the values. Let us summarize this video by listing the conditions to have rotating field f of theta and t equal f maximum sine omega t plus or minus theta. The conditions are balanced 3-phase supply voltage. We need 3-phase supply voltage equal in magnitude and shifted 120 degrees in time. The 3-phase winding should be symmetrical winding, each of which has an impedance Z. And to construct the 3-phase winding, you need to satisfy 3 conditions. Each pole should accommodate all phases, A, B, C, either go or return. The phase displacement between adjacent phases is 120 degree electrical. The start and finish of each phase is 180 degree electrical. Please remember, theta electric equal P over 2 theta mechanical. For example, 120 degree electrical equal for 4 pole machine 4 over 2 theta mechanical, so theta mechanical equals 60 degrees. So still you didn't cover here what is the speed of the rotating field. What will I watch in video number 2? In video number 2 we are going to watch or to cover the rotating speed and field nature. See you in the next video.